Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh and good day to everybody. My name is Amir Syawal bin Kamis. Today I will be presenting my research entitled The Development of Wheel-Over Mathematical Model to Reduce Cross-Track Error While Executing Turning Maneuver, Manoeuvring Simulation Using a VLCC Ship. So a little bit of background of the study. I think everybody still remember this incident where mighty MV Ever Given had completely blocked the Suez Canal for 6 days between 23 to 29 March 2021. So following the incident, the Suez Canal Authority had demanded 916 million USD compensation due to the blockage of the traffic. Okay, initial investigation suggested that the ship was mismaneuvered due to strong gusts of wind without ruling out the possibility of human error and equipment failure. And then approximately 3 months later, another mismaneuver incident happened in Kaohsiung, Taiwan. So what happened was the OCL Durban was trying to make a turn. Unfortunately, the vessel overshoot and hit YM Constancy, which was safely alongside at the time, and subsequently hit a crane and which tumbled onto another crane, which caused a huge catastrophe. So basically, a ship need to follow a passage plan or a voyage plan. So prior to a voyage, there will be a plan where it will conclude which course to take. Okay, so there will be a few courses. Okay, so there are connected courses where a ship need to follow. So ship need to follow this course, charted course, meticulously, and to avoid, going out from the course. So whenever a ship goes out from the course, this is what we call off-track maneuvering that can cause cross-track error. Okay, so there will be a distance between the course that intended to be followed and the actual course that the ship is following. So the distance between these two are called cross-track error. So staying on course is difficult, particularly while changing the ship's course, where the ship can overshoot, right? Overshoot from the planned track. So therefore, wheel-over point need to be accurately determined. Right. So suppose this is a ship, right? So this is a ship. It need to follow a voyage plan which consists of a series of connected courses, right? So two connected courses, connected, we call it a waypoint. So the point where the course is connected, we call it a waypoint or WPT. So if the ship don't know when to initiate the course alteration, what happens? The cross-track distance, okay, will start to develop, or the cross-track error will start to develop, which can cause the ship to run aground or maybe hit a jetty. Okay, so we don't want that, basically. Therefore, it is important for the wheel-over point to be accurately determined, so that the ship knows when to turn according to the ship's turning circle, right? And eventually end up on the next course. So that's the idea. So the problem statement and research aims. Okay, one of the method of determining wheel-over point is through advanced transfer technique, or ATT. So this research basically extend the efficacy analysis that was carried out and published by myself and my team, where we found that ATT is subjected to two gaps. The first gap is ATT is ineffective for change of course less than 20 degree. Why? Because whenever you are using equation provided by ATT, the wheelover point will come out as negative. Later on we will see what does it mean by positive wheelover point and negative wheelover point. And the second one is the final ship's heading differs from the charted direction, resulting in second overshoot. Later on we'll see visually what does it mean. So for this reason, using ATT as a basis, this research aims to build an improved mathematical model that can be used to determine an accurate wheelover point. Why? Because it is important to use mathematical model as a computer language in integrated branch navigation system, because in future everything will be autonomous. Alright, so the methodology. So the first step is to review and understand the ATT's gap. From there, we were able to develop a new mathematical model. And then after that, we went to the ship simulator to establish the course line in the simulator, where we carried out a maneuvering analysis using the ship simulator. So basically, what we did was we simulate what happened when we use F1 transfer technique and what happened when we use wheelover mathematical model, and then we compare these two data, specifically the cross-track error data, to see whether or not the cross-track error reduce. Okay, so in the analysis we use percentage change to see the declining trend of the error. Okay, first we review the ATT method. So this is ATT F1 transfer technique method, and this is the formula for F1 transfer technique. So there are two gaps that were identified with regard to ATT. The first one is whenever you use ATT to calculate wheelover point that is less than 20 degree, the value come out as negative. What does negative wheelover point means? Negative means the wheelover point is after the waypoint, which is illogical, right? So you're supposed to alter before waypoint. If you alter after the waypoint, it means you have already overshoot. Therefore, the ATT is not suitable to be used in autonomous ship, because the system itself, the algorithm itself, will tell the ship to overshoot first, then only alters, right? And then after that, as you can see here, the final ship's heading differ from the charted direction. As you can see here, this ship is heading this way, but this the intended course is this way, so it differs. So by understanding these two gaps, the idea is to make sure that the heading and the charted course is the same. Okay? Alright. So from there, we develop a new mathematical model. We call it wheelover mathematical model. And the final equation is this. So this is the distribution details, how the components fit each other, okay, according to the turning circle of the ship. Okay, for ship simulation, so the ship which was used for this simulation is a VLCC, or very large crude carrier. Okay, so this is the particular, and this is the turning circle for that ship. The result and discussion. So as you can see here, this is the result. What is the cross-track error that produced by ATT and wheelover point? First of all, let's see at the wheelover point itself. So if you use F1 transfer technique to calculate wheelover point, This is the first gap. For alteration to starboard or turning to the right, if your change of course is less than 20 degree, it will result in negative will over point. Same goes to port alteration or turning to the left. So for 10 and 20 degrees, the will over point resulted in negative value. Okay, but for will over point mathematical model, no negative value. At least we tackle one of the gaps first, and then we come to the cross-track error. So whenever you use event transfer technique, this is the cross-track error. When we use will over point mathematical model, this is the cross-track error. So it is important to highlight that this research was developed to reduce, to minimize the cross-track error. The error, we need to minimize the error. As much as we can, we want to make sure that error is zero. Okay, the error is supposed to be zero. So even though will over mathematical model developed in this research wasn't able to bring the error to zero, but we can see visually that a lot of improvement has been done. Okay, and you can see from the result, all negative. Okay, the cross-track error reduction percentage, all negative, meaning to say there is a declining trend, and very significant as well. So the negative percentage change value as seen in table 1 suggests that a significant reduction of the cross-track error was obtained during the manoeuvring analysis when study changed from ATT to will over point mathematical model. So the objective of this study is to reduce cross-track error that occurs due to the ship off-track manoeuvring or the attempt to bring the ship closer to the coastline. So the result indicate that for manoeuvring analysis with fully loading condition in the deep water area, the error was reduced by 61.1% to 95.7% for starboard alteration and 71.2% to 98.8% for port alteration. So it can be concluded that will over point mathematical model is able to provide a better track keeping function in terms of keeping the vessel closer to the line compared to event transfer technique. So the contribution of this research, first of all, it contributes to a novel mathematical model, an improved version, right? And then from the contribution can be also explained in 3 different viewpoints. The first one is contribution to the advancement of maritime knowledge. So the knowledge itself has been improved, new and improved mathematical model. Second of all, it supports Malaysian government initiative to promote green shipping. Why? Because whenever you reduce cross-track error, you actually reduce the distance travel. Whenever you reduce the distance travel, you are actually reducing the fuel consumption, and you will be able to reduce greenhouse gas emission, nitrogen oxide, NOx, sulfur dioxide. So as a direct result, you will be able to reduce all of this. So we are actually promoting green shipping. And finally, making significant impact on the future of shipping industry. So nowadays we are talking about autonomous ships, unmanned ship. So we need an improved mathematical model that can be used, can be served as an algorithm to the navigation. We cannot afford to have a negative will over point because we are basically telling the ship to overshoot first, then only alter. No, we cannot. Yeah, we can't afford to have that, right? So yeah, basically this research make a significant impact on the future of the shipping industry. Alright, I think that's all from me. Thank you for listening. Have a good day.